Okay, we've got a quiz on Friday. All right, and then I've got help. I'm available for help, or we got a homework due. Homework due on, well, it's Wednesday today, so Friday at 7 a.m. Okay, and I want to remind you that if you're having technical problems with the homework, I've had calls from several people that have Macs that have problems with the homework and things. They're intermittent. I've got some from the service rep. I have, or from the sales rep, I have some directions that could help. I don't know if they've helped or not. They help. Okay, they help. All right, so I can send you some directions for that. I can also extend deadlines and stuff to accommodate if you've been locked out of the system or had problems with that. So please let me know. Don't suffer in silence on that. Nobody should lose credit because of technology in here. Okay, so also Monday, Wednesdays, I'm available for appointments. Just let me know after class, 1 to 5 p.m. Today, let's not start until 2:15 p.m. Starts 2:15 p.m. today. I have an appointment with another faculty member and I need to get his input on something. So I'm not going to be able to jump around and help people while I do that. And then let's see, we've got a help session on Thursday at 7:30 p.m. on Google Meet. I think that's everything. Did I miss anything? Any questions? Okay. All right, so what we were doing is we were talking about gas laws last lecture. And so what we've done is worked through a bunch of different gas law equations, and we finally got into the big gas law equation that is PV is equal to nRT. Okay, PV equals nRT. And I will give you this equation on the test. But you can rearrange this equation to do anything you want, okay? So this is the only equation you need to know. If I wanted to do some sort of changes in gases, I raise the temperature, what happens to the volume? I lower the pressure, what happens to the volume? Things like that. You can just essentially say, okay, I've got one set of conditions, P1, V1 equals T1, right? Okay, whenever you do one of these change gases, if you're not adding molecules or something like that, which you almost never are, these are constant. R is a constant, it's our ideal gas constant, and the number of moles doesn't change, which is N. And so you'll have one set of conditions, you'll have another set of conditions. Like that, right? But if you aren't adding gas or taking gas away, these two things are the same, right? So I could rearrange both of these equations. So P1, V1, I'm going to divide both sides by T here. If I divide both sides by T, I end up with this is equal to NR. Remember our two NRs were equal, so that's also equal to P2, V2 equals T2. So I could just rewrite that. P1, V1 equals T1 over P2, V2 over T2. Okay, this is your combined gas law right here, but it just comes straight from this. Okay, we can get it right from here. And all the stuff in chemistry, or almost all the stuff, we'll have a little bit of calculus. You won't have to do the calculus, but calculus will be involved in its derivation later on in the class. Actually, probably next term. So when I say later in the class, I mean all of chemistry. But we'll have some things where calculus was involved in deriving things. You won't have to know the calculus. But in general, most of the things in chemistry or the chemistry we will see are just you make some assumptions, you have some simple law, and then you do a bunch of algebra to it, and then you get whatever it is, okay? So it's not magic. It's just assumptions about the natural world or some simple observations about the natural world, and then algebra. So last time we had done a problem right at the end that involved PV and RT, and so I wanted to do another problem. In terms of your the problems I gave you on the homework, I was careful not to give you anything that had a unit conversion going into PV nRT. So it was all in the right units. But your R, there are all sorts of values of R where the units change. But the R we're going to use a lot is going to be 0.0821 atmosphere times liters per mole Kelvin. Okay, remember, Kelvin is our temperature. That at 0 is absolute 0. There is no negative Kelvin. Okay, and the reason why that's great, or the reason why that's important, is if we think about the energy, the motion energy of molecules, and we think about, let's not use 0, but let's say we have 100 Kelvin and we have 200 Kelvin. If the temperature of something is 200 Kelvin, this is 2 times as much energy of motion. Okay, temperature is a measure of how much molecules are moving around. They could be rotating, they could be vibrating, but it's a measure of those sorts of things. Does that make sense? So that's why we use this Kelvin scale, because it starts at 0. So this, well, we're not going to say versus 0 because it'd be like infinite energy difference, right? But 100 versus 200 is going to be twice as much energy here. If we had 300, which is, closer to the temperature we're in, right? Temperature in right now is about 300 Kelvin. That'd be 3 times as much energy. All right, so the trick is that if this is your ideal gas constant, you don't have to memorize that. I will give that to you on quizzes and tests. But if that's the ideal gas constant, when I do PV nRT or anything with gases that involves this, I need to match units. So I need to be in atmospheres, liters, Kelvin, and moles. And I'm going to start giving you problems now where you have to be able to get into the right units. Okay, I'm not going to give you the right units. And we'll do this, a problem right here to start off. A container has 0.510 kilograms of argon at 0 degrees Celsius. Okay, and I'm just going to type these things because then I don't have to use my subscripts as much. And a volume, let's just, at the front of this sentence, let's make that better. A 800 milliliter container, because an 800 milliliter container has half a kilogram roughly of argon at 0 degrees Celsius. Which one are we missing of our gas law things? What is its pressure? So when I was in grad school, I used to go to step aerobics classes. I don't think step aerobics classes exist anymore. But I used to go to step aerobics classes, and we had this one instructor who would go up and she'd try to get people like going, yeah, and stuff like that. All right, you ready? Yeah. Okay. And nobody would do it because we were all lame. And I felt bad for her. She would go, yeah, and nobody would actually go, yeah, afterwards every time. But she had to do that. So I'm not saying you guys are lame by not giving answers, but All right, what is its pressure? Okay, so what is its pressure? So this is a PV nRT problem, right? And we're going to solve for pressure. So this is an easier one. Just looking at the equation, what would I do to this equation to make pressure be by itself? Yeah. Divide by the volume. Yes, thank you. So I'm going to divide both sides by the volume. I'm going to end up with this, right? You could put all the numbers in first and then solve for the pressure. That would be okay too if that's easier for you. So now my R, let's say the R at the top of the test is the one I've already given you. It's 0.0821 atmosphere liters per mole Kelvin. Okay. So what do I need to have? Which of these units that I'm given, which of these things that I'm given is in the right units? None of them. Okay? So let's go ahead and convert them. So I will give you your metric conversions. But if I have 0.518, well, 510, actually, I've got kilograms of argon. What do I need to go to? Not grams. I will need to go to grams to get to where I want to go, but I need to have moles of argon, right? Okay, and to do moles of argon, I need to use the molecular mass off the periodic table. Argon's 18, and I need to get to grams to do that, right? So if I look at the periodic table, this is pretty easy. I know that 38, is that 38? 39.95 grams of argon is equal to 1 mole of argon. And so now I can convert over. I've got 0.510 kilograms. How many grams in a kilogram? 1,000. So if I have 1,000 grams, that's 1 kilogram. Kilograms cancel with the kilograms. And if I have 39.95 grams of argon, that's 1 mole of argon. All right. So then we're going to go ahead and 5.10 times 1,000 divided by 39.95, and that gives me 12.76 moles of argon. Other people get that? Okay. 12.7, actually 7 moles of argon. And actually, my kilograms is 3 significant figures, so really it should be 12.8. Once again, just be close with your sig figs, and that's okay. All right, so there's my argon. Temperature. Right at the end of last class, we very quickly converted to Kelvin, right? Remember that your temperature in Kelvin is going to be equal to your temperature in Celsius plus 273 degrees. No, it's not just 273. Okay, so what we had is our temperature in Celsius up above is 0, right? So this is going to be easy, 273. I don't need my calculator for that. 273 degrees Kelvin. Or it might just be Kelvin. I can't remember. One of these things doesn't have degrees in it. Let's just say Kelvin. I'm not going to be taking off points for degrees or not degrees. All right, finally, we had one other unit there. Milliliters, right? How many milliliters in a liter? 800 milliliters, not 100, but 1,000. Close, right? Close enough for physics. Equals 1 liter. Okay, and so that's going to be 0.8 liters. And it's 800 milliliters. And the way I wrote it, it's one significant figure. Bad problem. Okay, we're at one significant figure at the end of this problem. All right, so we had PV is equal to, actually we rearranged it, right? We rearranged it. So now it's P is equal to nRT over V. See if we can get everything on screen here. Now we have our volume, we have our temperature, we have our moles. That's our N, our T, and our V. We're solving, and remember our R is 0.0821 atmospheres times liters over moles times Kelvin. You guys go ahead and solve it now. I wanted to do the unit conversions because we haven't done a lot of those recently. But I'm going to expect you can do those in the future if I give you the conversion factors. call me over if you have questions. And this is a great place to practice using your units, right? You've got the units in the constant there, in the ideal gas constant, and so they should all cancel except for your pressure unit. Okay, let's go ahead and look at this one. So I'll go ahead and solve it, and then you guys can tell me whether I got it right. We're going to go ahead and that goes there, this goes here, this goes here, and this goes here. Okay, and so we're going to go ahead and scoot down a little bit. I lost my ideal gas constant, but I fortunately have it memorized. So 12.8 moles times 0.0821 atmosphere liters times moles Kelvin. I'm gonna run out of some room here. Usually there's a way from looking for my bar, my little thing on the bottom that lets me deal with that. There we go. All right. So we've got that for, I need to know what is my temperature. My temperature is 273 Kelvin. Okay, and that's all going to be over a volume of 0.8 liters. All right, in terms of units, I can cancel a Kelvin on the top over a Kelvin on the bottom on the top. I can cancel a moles on the top over a moles on the bottom on the top. I have a liters on the top and a liters on the bottom. And I'm left with atmospheres, which is a unit of pressure, which is great because that's what I was looking for in the problem. So I'm going to take 12.8 times 0.0821 times 273 divided by 0.8, and I get 359. Okay, so 359 atmospheres. Holy cow! And for correct sig figs, that's actually going to be 4 atmospheres because there was only one sig fig there. Okay. Yes. It would be 400. Thank you. Okay, great. All right, questions on that? So that's how you use that equation, and also you may not have all your units in the right format. If I gave you this on a quiz, I wouldn't want you spending forever converting units, so I might have 1. Maybe I would do 2 for that. All right, so what I'm going to do now is I'm going to go on and I want to talk about a concept that gets used, or it's a term or a definition that gets used often when we're talking about gases. It also then gets used going on in all sorts of things in chemistry. And this ideal gas constant thing we've got here, like I said, there's lots of different units. It keeps showing up. It's the ideal gas constant. You're not working, you'll be doing something, you'll be not working with gases at all, and there it is again. So it's one of those things that's important. It's related to a law of nature, and it shows up again and again and again in our equations in chemistry. What we've got is we've got this thing called standard pressure and temperature. Okay, and later on we'll have something more that more broadly includes this that's called standard conditions. Okay, so standard pressure and temperature, sometimes it gets called STP. And what that is that's a pressure of 1 bar. And a bar is where is this thing? 0.987 atmospheres of pressure. And a temperature of 0 degrees Celsius. Okay, so that's what standard conditions are, and that's going to be 273 Kelvin. That'll help you remember that. Okay, so these is standard temperature and pressure. And what was interesting about this last night when I was in your book looking at this is I was like, what the heck? Standard pressure isn't 1 atm, so I'm sure you think I'm very old, and I'm pretty old. But it always was 1 atmosphere of pressure. So I don't know why I don't even know why somebody made up this bar thing being different. They didn't make that up during my lifetime. But it's interesting that even this thing has changed around a little bit. It's a little loose what you see. So you may see at some point standard pressure be 1 atmosphere. Not your book. I'm following your book. Okay. And actually, if you look out at the official societies, this is what it is. So it's interesting that even these little things wiggle around a little bit over time. But somebody talks about standard temperature and standard conditions, you'll put in 1 bar, or you could put in 1 atmosphere. I don't know if you've looked at the book at all. We've got a whole mess of different units for pressure, and there's just no helping it. So in your tires, what's the pressure? Let's talk about other units of pressure, just so you know what they are, because you're going to see them. If you see them and they're on a homework problem, look up the conversion factor, okay, and do that. And then if it's on a test or something, I'll give you the conversion factor. So let's talk about other pressure units. So other than what we have up above, we've already talked about a couple. What were they when we had the manometer? So remember, we had a manometer and we measured pressure by millimeters of mercury, right? How high the mercury was. And then that actually had another name, and that was torr, which I would think was named after somebody, but I see it lowercase. So we've got torr. When you fill your tires, what's the pressure you worry about? PSI, pounds per square inch. Okay. We also have kilopascals. People talk about kilopascals. Okay. And pascals is probably the most reasonable unit of pressure. I think the bar comes from 100 kilopascals because it's actually defined based on physics units, as opposed to some units people came up with. But regardless of what these units are, they're just all different easy to convert between them. They're not different things inherently. They all have to do with how hard molecules, how fast molecules are moving and how hard they're hitting a surface, right? So how fast determines if I have molecules in a container. It determines how much they're flying around and how often they hit the surface, right? And also if they're going faster, they hit it harder. So I want you to try to think about what the molecules are doing whenever you can. Molecules in the atoms in this case. Questions? All right, so then we're going to go on and we're going to start talking about, oh, actually, I've got densities of gases next. Let's talk about densities of gases real quick. All right, what is density? Density is equal to what? Mass over volume, right. So density is equal to mass over volume. So when we talk about gases, we can talk about the density of a gas, and this isn't a different equation at all, but what we can do is we can talk about the molar mass over the molar volume. Okay? We can think about what's the volume of a mole at whatever conditions we're talking about. And so if we think about at STP, at standard conditions, at STP, standard volume and pressure, or not standard volume, standard temperature and pressure, molar volume equals, with this bar thing, it ends up being 24.5 liters. Okay? So you could calculate that using your PV is equal to nRT, right, and putting standard conditions in. But so that what that means is that if we want to figure out the density of a gas, we just need to look up its molar mass. All right, and most of our gases, we could calculate them from the periodic table, right, depending on what they are. But so let's go ahead and so the density of helium is going to be, under standard conditions, just do a little STP here, is going to be 24.05 liters with my molar mass up above. What's my molar mass for helium? It's 4, right? Off the periodic table. So helium is just He. It's by itself. Why is it by itself? Why don't I have He2? Like H2? Because it's a noble gas. It doesn't want to react with anything else, right? Remember, the noble gases are all happy as is, so it's hard to get them to react with anything. As you go down the noble gases, you do get some things to react with things. But mostly, they don't want to do that. They're not made more stable. So we've got 4.00, it looks like, grams. And so for helium, if I take 4 and I divide it by 24.5, I'm going to get 16, let's see, I've got 3 significant figures, 0.3 grams per liter is my density. Okay, what is the density of nitrogen? Nitrogen gas is what's mostly in the air around us. So the density of the air around us is mostly given by nitrogen gas. We may talk later about a weighted average for it. We may not. But I think we can compare the density of helium to the density of nitrogen and make some conclusions. Go ahead and calculate what the density of nitrogen should be. What was that? We're doing and 2 nitrogens, yes. Because they're stuck together. Okay, so let's go ahead with that. So nitrogens, it's 2 nitrogens, right? 2 times nitrogen, which is going to be for my molar mass, is 2 times 14.00, 14.01, is it? 14.01, 001. Let me try that again. It's 14.01, okay? So 28.02 grams per mole, right? So I can go ahead and put in 28.02 grams here. .02 divided by 24.5. And I get 1.1, what have I got? 3 significant figures, 14 grams per liter out of that. That's what you should have gotten. Does that make sense? Okay, so let's look at that though. So you take a, let's take an example here. Last night when I got home, I made myself, I poured myself a sangria, and I put some ice in it, a glass, and I poured myself a sangria, and the ice floated up to the top of the glass. Why did the ice float up to the top of the glass? Because it's less dense. You started with the right answer. So it's less dense because ice, when water forms ice, it expands. Okay. So that's what happens in a liquid, right? That's why when you jump in the pool and you don't blow the air out of your lungs, right? If you jump in the air, you put air in your lungs, you jump in a pool, pretty much everybody floats. Okay, because you are less dense than the water around you. Certainly in salt water, if you go in the ocean, you float. Okay. So that's why you float. Same thing for gases. What happens if I put helium in a balloon? And then I let go of the balloon. The balloon takes off, right? If I don't have it on a string, it just takes off and keeps going up. And what's going on there is the density of that balloon, including the weight of the balloon itself, is less than the density of air. Okay? And that's not perfect for the density of air, but air is like 79% oxygen. Not oxygen, nitrogen. Okay? So we can use this to explain things like why do those balloons float? Okay? And the point is you just need to have enough helium in that balloon that when you take into account how much the balloon itself weighs, that overall for the volume it's taking up, it has a density less than that. Questions? Yes?
So like when it comes to cutting density, is 24.5 going to be like a constant?
This is going to be a constant if we are at standard conditions. Okay, if somebody gave you different conditions, you might have to calculate what that is. So don't memorize 24.5 liters, and I won't give it to you, but you might have something where you can use PBNRT to figure out what the volume of a gas is. And there are more complicated ways to ask this question. But that's how we're going to use the density here. Other questions? Okay. Then we are going to go on and talk about partial pressures. And before we talk about partial pressures, I remember they probably told me why it was important, or gave me some examples. And these partial pressures are, especially if you are health career bound here, partial pressures are important. They're going to determine how much gas goes into liquids, and your blood is liquid, right? So partial pressures are actually important for thinking about human health and what's going on. We're going to have to add another law that we're not talking, called Henry's Law, that we're not going to talk about today, to that before we actually get into where we talk about dissolving gases and liquids. However, I am going to talk about partial pressures with that concept sort of generally. So did anybody know anything about deep sea diving and dangers associated with it? And you're probably going to come up with something I don't want to talk about first. But anybody want to give me? Go ahead, Madeline. Okay, so you get the bends. Okay, and so the bends are actually, I think the bends are when you have bubbles of nitrogen coming out of your blood. But there's another thing you have to worry about. Tiffany, do you have it?
The water pressures.
Yeah, the water pressure is intense, and that's part of it. Part of where we're going to have an issue with partial pressures here. You guys ever heard of oxygen toxicity? So you can get too much oxygen. All right. And so right now we are under 20, there's 21% oxygen in the room with us with 20 at 1 atmosphere roughly. Okay, we're at a little higher elevation. We're not going to worry about that. Let's say it's 1 atmosphere. So we've got 21% oxygen, O2 in the air. Okay, and I'm going to give you a little equation that we're going to make more formal in a bit. But if I take that and make that a fraction, so 0.21% of the air is oxygen, and I take that times by 1 atmosphere, the pressure of oxygen on us, remember, pressure is things bouncing off, right? So the pressure of those oxygen molecules bouncing off to us, what we would call the partial pressure, is going to be 0.21 atmospheres. Okay, does that concept sort of make sense? All right. So that's where we're at. We're operating fine right now. Now, if we were to go into the water, every 30 feet or 31 feet-ish that you would go down to the water, you'd be under an extra atmosphere of pressure. Essentially, water pressure pushing down on you. So that calm the water pressure down on you, the atmospheres go up. And so if I was to dive down 31 feet, I would be under double that pressure. I'd be 2 atmospheres, right? So at 31 feet, I'm going to have 2 atmospheres of pressure. And if I'm breathing air from a tank at that point, that's just regular air. Now I'm going to have 0.42 atmospheres of partial pressure of oxygen pressing around in my lungs and things like that. This affects how much, the more pressure there is, think about this. I've got this much pressure of oxygen in my lungs. It's bouncing off my blood vessels. And if it's bouncing off my blood vessels harder, it's probably going to put more oxygen into my blood, right? All right. So oxygen is good up to a point. And so I was reading about this last night. I forgot who the official society is, but I'm just going to write it as some diving society. So some expert diving society, because I don't remember the name. Okay. The folks I was reading about it, I wasn't even reading on Reddit. The folks I was reading about it were actually, they were official divers. It was an expert discussion. Some expert diving society says you should not exceed 1.4 atmospheres of partial pressure of oxygen. Or you should not, let's say, it says that, not you, that the partial pressure of oxygen should not exceed 1.4 atmospheres. Okay. What happens at this, you get oxygen toxicity and you can get convulsions. Okay, so I was also reading a paper that wasn't given, I was reading an actual primary literature paper trying to figure out what we needed to worry about. And I was trying to find this 1.4 number, and they were using weird units, and I was having a hard time getting it. But what they said for the convulsions, I thought the comment was pretty interesting, I guess is an understatement, is they said convulsions when you're deep sea diving are usually fatal, is what they said. So I think so you go into convulsions, people don't get to you in time. I don't know whether the convulsions themselves are fatal or just that you're not actually handling your breathing apparatus at that point because you can't do that. You also get a little loopy before that happens, right? You get a little loopy, you're not making good decisions. So it's important not to exceed that. So let's go ahead and let's think about that. So this is, I just introduced this not in the way the book did, and that's okay, I didn't mean to. But this is, so we talk about this would be the partial pressure of oxygen. So you've got the pressure of nitrogen, all that other stuff going on as well, right? And the bends, the bends are a problem in terms of nitrogen. There's problems with nitrogen and coming back up because you've got nitrogen dissolved in your blood. And if you change and more dissolves at a higher pressure, and so if you come up and you release the pressure too fast, you get air bubbles in your blood. They block capillaries, so you can end up with you can have a stroke from that sort of thing. That's the partial pressure of oxygen, and this is the mole fraction of oxygen. So what that means is when we say that air is 21% oxygen, we mean that 21% of the molecules are oxygen, not 21% of the mass, because they all have different masses, right? O2 has a different mass than N2 has a different mass than carbon dioxide, which is part of, not a huge component, but a component of air. Argon is actually a pretty decent component of air, and none of these things, they all have different masses. So it matters whether we're talking about mole percent or mass percent. Okay. So, but we're going to be talking about mole percent here. All right, so we have an equation. I'm going to call this mole percent thing. X1 is equal to mole fraction, because we're expressing it as a fraction there. Okay, and that's going to be equal to the number of moles of whatever this 1 is. Okay, this could be O2 over the total number of moles. And when we think about pressures, the total pressure, each of these gases is going to exert the same amount of pressure per molecule. So, like that. Okay, so the partial pressure is equal. So if we think about the partial pressure here, let's go ahead and do it for oxygen. That's the general equation. So we can think about, we use X for this. I'm actually using the thing, is the mole fraction of O2, and that's equal to the number of moles of O2 over the total number of moles. And that's equal, that is also equal to the pressure of that oxygen over the pressure total. Does that make sense, what we're doing there? Okay, so when we talk about 21% oxygen, what we're saying is, or we talk about a mole fraction of 0.21%, we say that air is 21% oxygen. Right? We could do this with percentages. We can say it's 21% oxygen, and the total is 100%, right, of everything. Nitrogen, oxygen, and some other things. Does that make sense? Okay. What this tells us is that the pressure of a gas, if this is true, and it is, it tells us that any given gas, whatever it is, exerts the same amount of pressure per mole. Okay, so if I have hydrogen gas and I have oxygen gas in a container, right? The hydrogen, which one is more massive? What was it? I have hydrogen gas, I have H2, and I have oxygen gas in a container. And the molecules are whipping around. Which of those is more massive, the oxygen or the hydrogen? Oxygen. Oxygen, right? Oxygen is 16 times as massive, okay? Right? So they're whipping around. Think about, let's think about something here. So they all have the same energy, okay? But one is more massive than the other. So think about if you go out and let's say you want to push your, let's say you want to push your bicycle, okay? You want to push your bicycle to your dorm, okay? You're going to push a bicycle dorm. How's that going to go? Think about how much energy that would take. You've got a certain amount of energy, right? So you're going to push that bicycle to your dorm as fast as you can. All right. Now you're going to push your car to your dorm as fast as you can. Which is going to move faster? The bike is going to move faster. But you're putting the same. If you're doing it as fast as you can, you're putting the same energy in, right? So this is going to move slower. Okay. But it has the same energy, so it's going to actually impact, it's going to give an impact in terms of pressure. This is going to move faster, it's going to hit more often, right? This has got the same energy, but it's more massive, right? And so it hits harder when it hits. This has the same energy, it's bouncing, and it's moving faster, it hits softer when it hits, but it hits more often. Does that make sense? All right, so, and it works out that is such that any gas will exert the same amount of pressure per molecule, okay, or per mole of molecules. Questions on that concept? Okay. So, we can ask a question now. We've got an equation. And we could say, and we're going to use my 30 feet per atmosphere pressure. So at what depth should a deep sea diver stop using regular air? Okay, regular air is 21% oxygen. So how would we answer this? And we're going to say 30 feet of water depth adds 1 atmosphere of pressure, of total pressure. Okay? So obviously a very important problem, very important thing you want to be able to solve if you don't want to die if you're deep sea diving. Okay? What they do for this is they switch to different air mixtures. I think they switch from one to the other as you're going down. Okay? But you switch to a mixture that contains less oxygen. At some point, have you guys ever seen things where they switch to helium? Folks that are really doing it, like they're down at some submarine at really deep levels, they're talking in high squeaky voices because they're putting helium in their tanks and a little bit of oxygen. You guys haven't seen that? Okay. Well, they do switch to helium because helium does not dissolve in your blood as well, so you have less problems with the nitrogen. So what do we got here? We've got an equation. We know that the mole fraction is going to be equal to the partial pressure of oxygen, right, over the total pressure of air, of our mixture. All right, so what I'm going to do here is I want to solve for, remember, what was our safe limit for oxygen? It was 1.4 atmospheres is the safe level. You don't need to memorize this. Pressure, I'm going to say partial pressure of oxygen. Okay, it's the limit, right? So I'm going to put that here. 1.4 atmospheres goes above my pressure total. I don't know what my pressure total is going to be, right? What pressure total is going to result in my be hitting this 1.4 atmospheres, and I better not go below that. And so then X1 is going to be our mole fraction, which is 0.21, right? 21% oxygen. Is this making sense? How we're using this? Okay. So then we're going to solve for pressure total. I can multiply both sides of this equation by pressure total. And then I'm going to get these pressure totals canceling. And can you see that if I divide both sides now by my mole fraction, we'll do it in separate color. Those cancel. And so my pressure total is going to be equal to this, right? So 1.4 divided by 2.21, I get 6.7 atmospheres. Okay? They said 7 atmospheres of pressure. You guys all lost? Is that what's going on here? No? Okay. 7 atmospheres of pressure. And what did we say? We said 30 feet was 1 atmosphere of pressure, right? And it's 1 additional atmosphere, 30 feet of water. So it's 1 additional atmosphere. So it's actually 5.7 atmospheres we're worried about, because we're under 1 atmosphere right now. If I go down 30 feet, I'm now under 2 atmospheres. That make sense? So what we would just, if we want to put this into a depth, then we'd say, I've got 5.2 atmospheres. How many feet is that end up being? 1 atmosphere is equal to 30 feet. And so 5.7 times 30 equals 171 feet.
Is it 5.7 or 6.7?
It is not 6.7. Let's talk, good question. Let's talk about why. So that's 6 atmospheres. So what that 6 atmospheres is that's going to be 1 atmosphere for sea level, right? Before I dive. It's the atmosphere we're under right now, plus 5.7 atmospheres of water pressure. Okay? So if I'm diving, I better not go more than 171 feet down with a normal air tank. I need to have another air tank, type of air tank I'm going to switch to. And I don't know all the details of it, but this is something that somebody who is doing this diving has to really be concerned with. Does that make sense? Okay. If somebody has, let me see if I can get it, if there's another good concept in here that we should talk about. I have a bunch of problems, and I will give you some. Let's work one problem. Okay. So let's try another type of problem of this. A gas cylinder, this could be, contains let's say a 24-liter gas cylinder. There we got our volume. Gas cylinder contains 8 moles, 8.0 moles of nitrogen, and 2 moles of oxygen. If the temperature is 37 degrees, what is the total pressure and what is the partial pressure of each gas. That's body temperature. Okay, I'm trying to squeeze this in so I can give you a problem. I'll fix the spelling of cylinder in a second there. But let's make sure we're going to write out. So we're going to start out using PV nRT to figure out the total pressure, right? PV is equal to nRT. I'm going to check my, do I have three? So I have to have three of these things. I have to have three of pressure, moles, volume, and temperature. I have moles. I have my total moles, right? It's going to be 10. I have my temperature. I have a volume, so I can do the pressure. Okay. So pressure, if I divide both sides of my PV nRT equation by V, I'm going to end up with nRT over V, right? So I'm going to go with that. My total moles here is 10. And I'm just going to work this one because we're really short on time. So I've got 10 moles, right? My ideal gas constant, I look up at the top of my test and I see it's 8.21 atmosphere liters per mole Kelvin. Okay, my temperature is 37 degrees. What's wrong with that? Degrees Celsius. It needs to be Kelvin. Because of time, so I'm going to add 273 to it. Okay, that's 310. I have it memorized. Okay, a biochemist, I love body temperature. And then my volume is 24 liters. I'm going to throw this into my calculator. 10 times 0.0821 times 310 divided by 24. If I had more time, I would carefully show you how you can cancel your units. And our total pressure is going to be 10. How many sig figs do we have here? I had 2 sig figs on these moles, right? So 10. It's going to round up to 11. It's going to be 11 atmospheres is what I'm left with for units. Okay, that's my total pressure. I'll do one partial pressure. All right, my partial pressure is going to be equal to, remember my mole fraction is equal to my moles of one thing. So let's do moles of nitrogen over my moles total. Okay, and that's going to be equal to my pressure of nitrogen over my pressure total. So I can actually take this thing and use that. My moles total is 10, right? My moles of nitrogen was 8 moles of N2, and that's going to be equal to the pressure of N2 over my total pressure that we just figured out was 11 atm. So my pressure, so if I solve for this, okay, which would be, I'd multiply, I'm going to just do this. I'm sorry, I'm not going to do the algebra here. I'm going to do this divided by this. So I multiply these together, I divide by that. And I end up with 88 divided by 10, or 8.8 atmospheres. All right, and I just skipped the algebra there and did it very quickly. Okay? Questions? If you have questions, come on up. I know you guys have classes to go to. Do you want me to go through them?
I'll talk to you after everybody else finishes talking to you.
Okay, you know it's later, right? It can't. Okay, so I can't, like, not until 2:15? Yeah. You want to talk now?
Oh, yeah, well, yeah.
Okay.
I'll just finish class after, I'll just tell her.